Hello and welcome to the first session of our Enduro India workshop here at Simscale in collaboration with Enduro Student India. My name is Milad, I'm Academic Program Manager from Simscale, and it's a big honor for me today to help you with your journey through the world of simulation. Great. First of all, I would say we should take a look at our today's agenda, and sorry for the delay, we had some technical problems. So what are we going to do today? First of all, I would like to talk with you about the idea of this webinar and this workshop series. Just after that, you will get the introduction to the fundamentals of finite element simulation. And just after that, my colleague Krishna will join and show you how to leverage our free simulation platform for car design. After that, we will show you a homework assignment and we will have time for a Q&A. Yes, so let's start to talk about today's webinar or today's workshop series. And as you know, this workshop series is conducted by Simscale in collaboration with Enduro Student India. And the reason why we are organizing this workshop is that we want to enable every student and participant of Enduro Student India to leverage engineering simulation for their own design. And the idea is that we will have two sessions. One session is today, the next session is next week, an online session. And during this online session, we will show you and teach you everything you need to know to get started with engineering simulation. And every session comes with an optional homework assignment, which is about creating a simulation on your own. And you can share this homework with us using a form at simscale.com, and sharing this homework will qualify you for a free certification. So taking part of this workshop is not only good if you want to learn something, but also if you want to maybe get some documents and some certifications about your skills. Just because we got a lot of questions. First of all, will this workshop be recorded? Yes, as far as I know, our colleagues from Enduro Student India are recording this workshop, and we will provide registrants with recording soon, and later on, I think after a couple of weeks, we will even make this recording available to everyone. We will show you during this workshop or during this webinar how to set up a simulation on your own. However, please do not start to simulate during the workshop. I really think we should use this time we have to discuss about questions, and you will have more than enough time after this live webinar to prepare your homework. For sure, you will need some support, or maybe you will need some support during this course. And whenever you need help, just check out our free forum on simscale.com/forum. And there we have a dedicated section just about Enduro Student India. And there you can ask all your questions related to our tools, to the platform, or also about the organization of the workshop, for example. Great. Before we start to talk about our actual topic, I would like to introduce Simscale very quickly. So Simscale, we are a company from Munich, Germany, and we are a spin-off of Technical University Munich. And this company was founded 4 years ago with the vision to democratize engineering simulation. But what does it mean? I'm quite sure during your studies you have heard about engineering simulation like finite element analysis or computational fluid dynamics. And if you think about the opportunities that tools like this give to you, it's really great. You can do virtual prototyping, you can test something, you don't need to manufacture a prototype anymore. So it has a potential to save a lot of time, resources, and money. However, simulation is still not adopted in every industry. And the reason is that traditional simulation tools came with a lot of overhead. You needed a lot of money to buy the initial software license and hardware. You needed a lot of infrastructure which needed to be maintained to be able to access the software. And finally, the tools were designed for experts, so it was very hard to get started. And Simscale is basically a fully fledged 3D simulation platform which runs completely in your web browser. So you need not to install anything. You don't need any kind of own hardware. The only thing you need is a standard web browser and the internet connection. Everything else will be delivered through the cloud to your desktop. And another great thing about Simscale is our pricing model, which means that Simscale is absolutely free. We have a community pricing model, and this means that basically you can see here on the slide the 3 plans we're offering. And all those 3 plans have exactly the same features, the same simulation tools, the same accuracy, even the same computing hardware we're using. The only difference is, as long as you're using a free community plan, all your projects, simulation projects, will become public projects, which other users can import and use as a starting point for their own simulation. And however, this community tool gives you a bunch of very powerful free tools which you can use. And in addition to that, another big advantage of Simscale is that we are more than just another simulation software provider. We are a simulation ecosystem, and I talked to you about this public projects, and we have a lot of public projects. We have more than 10,000 different simulation projects on our platform. And here you can just see an overview about all the applications we can cover with Simscale. So starting with for example, external aerodynamics of an airplane, internal flow of a compressor, structural behavior of suspension, what we'll also talk about later, and so on and so on. And the best thing is that Simscale is, as I mentioned, more than a platform. We are a simulation ecosystem, which means we bring together content, tools, and people. And now let's talk about the best part of my presentation for your ears, maybe. We really like Enduro Student India, and we really think that you guys are doing a great job. And we really think that simulation could help you to even design much better cars. Therefore, we would like to offer all teams which are taking part as Enduro Student India a free sponsorship of the team, which includes a professional plan which gives them the possibility to create private projects, which I think is essential if you're taking part in a design competition. We will also give you free access to our learning resources. We have a lot of online courses which usually you have to pay for, and you can access them for free as a sponsored team. We have some dedicated support on our forum, but also with our engineers who can help you to get started. And in the future, we'll offer a lot of exclusive event and trainings dedicated for the application of simulation and Simscale in Enduro Student India. Basically, there are just 3 requirements. The first requirement is that you are an enrolled student. The second requirement is that you are a member of an official team. And the third requirement is that you have to submit the 2 homework assignments. And if you fulfill all 3 requirements, we will sponsor your team with a free professional subscription. In order to get sponsored by us, first of all, please create a free account on simscale.com. Submit the homework, the 2 homeworks related to the session within the deadline. So the homework which of this week until next week, and the homework of next week until the week after the next week. And once this is done, we will send you some weeks after the last workshop session your certification, as well as a sponsoring form. And you just need to fill out the sponsoring form, sign it, mail it back to us or scan it, and then you will receive your professional subscription. Please note that we will only offer 1 professional account per team, so therefore please talk to your colleagues who will apply for the sponsorship. Great, and now I think we talked a lot about what this workshop is about and what Simscale is doing, but I think you basically joined to learn something about FEA. And today's topic is suspension design analysis with FEA. And just to make it clear, the aim of this webinar is that after this webinar, you will be able to create a simulation of your own suspension. And since you should really learn and understand what you're doing, we need to talk about some fundamentals first. And in this case, about the fundamentals of finite element analysis. So what is FEA about? As you know, I think most of you are studying engineering, science, or something related. most of processes which are happening in nature this can be described by partial differential equations, and this is a continuum of problems. And I don't want to go too deep into math, but what means partial differential equation? Just take a look at the equation here on my screen. It's not important what this equation is saying, but what you can see is here we have the equation which is including, for example, the change of something against something, and this is a partial differential. So, for example, this function is depending on x, y, z, and t, on 3 coordinates and the time, and the overall equation is made of parts and terms which are only depending on the chain against one of these variables. So the change of this term against x, for example. And a big problem we have, or basically 2 problems. First of all, we cannot solve these equations analytically. They are very complex. For some very simple phenomena, you can get an analytic solution. But for all practical and real-world phenomena, it's not possible. And the other problem is, if you cannot solve it analytically, you have to solve it numerically. And if you solve it numerically, you have to use a computer, which means you have somehow limited memory and computational power. And basically, what the idea of FEA is to take these equations, which are describing, for example, heat distribution inside a solid object, and to solve the equation using functions which give us a very good approximation solution. And since we have today a lot of computing power, we can use very large computers to solve these very large linear systems, which will be created when applying FEA to this kind of problems. And this is the most important thing you have to understand. These partial differential equations, they are describing the real world. And we are converting them into this linear equations which we can solve. And let's make this more vivid, because I think that was very theoretical. So let's take a look at the image you can see right now, and this is a hook. And just imagine we want to make a stress analysis of this hook. And in the real world, we have this hook, which is a continuum. And inside this, on this continuum, we have a load, a lot of loads. And if you want to solve with the aid of FEA, we have to convert this into a discretized model, which means, first of all, we need to find a number of degrees of freedom. And then we will split our model into a lot of small elements. And we cannot calculate, or we don't know what happens for this complex shape of the hook, but for the simple shapes, which we call, by the way, elements, we can solve them. These elements, and that's, by the way, why it's called finite elements, because they are finite, not infinite. It's just a small piece of a structure. And in the end, we can now calculate the structural behavior of every element, and these elements are connected to each other by the nodes. And this helps us to convert a continuum problem into a discretized model. And now let's just take a look at the general FEA process. So first of all, we have to discretize the continuum. We have to select interpolation functions, find the element properties, assemble the equations, solve the global equation system, and compute additional results. And the first part, discretize the continuum and select the interpolation function. This is what we call meshing, a very important part, which is about converting your CAD design model into a numerical model, which we can use for our simulation. And I just like to make sure what a mesh basically is, or what meshing basically means. And let's take a look at the slide here. On the top, you can see, on both cases, we'll take a look at the beam structure. On the top, you can see the analytical version of a beam. I'm quite sure you did something similar to this at school. And below, you can find a finite element representation of this beam structure. And as you know, for this kind of beams, there are already analytical equations and solutions which you can use to calculate stress distribution, displacement, etc. But if we take a finite element representation, we will represent this elastic bar, this beam, by small bar elements like here. And these elements are connected with nodes. And as you know, this bar has some properties. And one of them is the length of a bar. We have the elastic modulus and the cross-sectional area, since this is a 1D model. And now if we take a look at the model, we can get some relation between all these variables, because as you know from the displacement and the elastic modulus, I can calculate the force. So A divided by L, it's the cross-section of the bar divided by the length of the bar. It's like, you could say in the end, how much cross-section per length. It's something like a density in the end. Then we have E, which is the Young's modulus, and U1 minus U2 is the displacement of the point U. And we have the same for the F's, force F2, and this gives us two equations. I don't want to go into this too much in detail, but there's a very nice YouTube video you should take a look at, where someone is performing this derivation. And in the end, this is maybe not something which is completely related to what we will do in the next couple of minutes, but to understand this is very important, because it will give you a good idea of what FEA is basically about. And together with some constitutive equations, we can convert this into a system of linear equations. And if you take a look at these two equations, we can also write them that way. And if you take a look at that, this is a very important thing to understand. So give me the chance to mark something. So, okay, take a look. What you can see here, U1, U2, this is what we could call a nodal displacement vector. So this is the displacement of your meshing points of your nodes. This matrix K is a stiffness matrix, because in the end, it's just describing the topology of our geometry. If you multiply this A multiplied with E divided by L with K, the stiffness matrix, you will get the equations. And on the right side, we can see a force or load vector. And to summarize this, what we can say is stiffness matrix multiplied with nodal displacement vector will give us a force. And that is what we do at FEA. We know the stiffness matrix, we know the force and load vector, and what we want to get is U, the nodal displacement vector, the solution of our simulation. And this can be really hard, because this nodal displacement vector is unknown, as I mentioned. And now we use numerical schemes and algorithms to solve U. And this kind of solution will look a little bit weird, because let's just, if we take a look, we can solve U by calculating the inverse of K multiplied with F. And if we take a look, here you can see the analytic comparison between the analytic and numerical results. And you can see that right now it's basically exactly the same, especially on the nodes. And if you take a closer look, you will see that the result is not continuous. Because if we take a look at the strain right now, we will get this kind of stairway structure. And this is related to the fact that we're using shape functions to interpolate the solution between discrete values obtained at the mesh nodes. Just imagine, right now we are only calculating displacement and stress for the points of the nodes. And this using shape function means that we get this kind of discrete result. So for every node, we have a result which is constant until we reach the boundary of the next node. And this is very important to understand, because in the end, the quality of your simulation mainly depends also on how you modeled it. And in the end, you need to know where are the limitations of FEA. And one of them is very much related to the fact that we're using shape functions here. Last but not least, let's just take a look at general FEA process. And the full steps. So first of all, we need a physical problem. This can be, for example, that we don't want our suspension to crack. Based on this physical problem, we will create a mathematical model. And this mathematical model will be converted to a numerical model. And if the answer makes sense, then we're happy. And if not, we have to change something. And most of the time, when you get a result which is not looking very good, you will be facing two kind of problems. The first problem is that your simulation makes no sense in terms of physics, for example, that you get stress, which is, for example, very, very high, unusually high. And this can be related that you really have a problem with your simulation. For example, just imagine if you put your nodes, or if you increase the density in an area where you don't have a lot of change of stress, and you have a very coarse mesh somewhere, for example, where there is a high change of stress, it can happen that your simulation results are crap, and then you have to improve the mathematical model, which means, for example, change the mesh or the boundary condition or something else. And sometimes the problem is, for example, the design is not good. For example, simulation is crashing because the design would not last with this boundary conditions. Then you have to update your physical problem. Yes, there's just one thing I would like to talk with you before my colleague Krishna will take over and do a live demonstration how to leverage Simscale FEA for Enduro Student India. And I will talk with you about something else which is very important, which we call CAD preparation. Because most of the time you need to spend as a simulation engineer to prepare the CAD model for simulation. And I will just, for as inspiration, show you some examples, and I hope that it will help you. And first of all, take a look at the left side. And here you can see we have a very large machine assembly. And the original CAD model is made out of 2,000 or more than 2,600 single bodies. We have more than 208 short edges. Short edges means in this case that the edge is really short, so below several millimeters. And most of the time, these short edges are not designed on purpose, but maybe because of bad surface quality or some problems with the CAD model. Or let's say if you don't have a clean model, and the same problem can result with small faces or silver faces. And just to load this model, our CAD system, like 360 seconds, so like about 6 minutes. And on the right side, you can see the final model we used for the simulation. First of all, reduce the number of bodies to 60. We have no short edges, no small faces, no silver faces, and we can load the model into our CAD system or Simscale within a fraction of a second. And what exactly did we do to improve this model? And why did we do it? First of all, you should consider every detail which you don't remove from your model needs to be meshed and will be considered for the simulation. And especially if you have a lot of small parts, they will maybe not affect the overall structural behavior of the object you want to investigate, but it will add a lot of additional effort to resolve it and to mesh it. So a simple geometry will deliver a faster and better mesh. Another very important point is that it can help you massively to simplify your simulation setup independent from the mesh. Example given. Let's say we have a part which is symmetric, and we just take a part of it. Let's say it's a half of it. We only have to define half of the context, half of the middle, half of the boundary conditions. End of to be loaded and computed, and this is depending for sure also on the mesh result size. First of all, the very important lesson: model is a critical part. This is, I would say, the most important recommendation I can to you. And let me give you again a very good, or on the slide you can again see a very good example. This is a very large crane, I think, or not a crane, but excavator. And if you take a look, let's say we are interested in finding out how we can optimize this design. The most critical part is this part here. And if this part fails, everything else will fail. And from my experience, we know that as this part is not failing, nothing else will fail. Then you should focus only, first of all, and investigate this part. And something I already talked about is that it's very important to take advantage of symmetry. For example, it's even symmetric in 2 dimensions. So we need 1/4 of the model form simulation. That will reduce the mesh size by 75%, as well as the numbers of boundary conditions we need to set. A very important point is the featuring. What you can see here is a part of, I think, assembly. And for the real capital, for sure, this is modeled as in the original model as a bolted joint. If we want to do, for example, a simulation here, and this is again a very good example for critical parts only. We know that the last thing which will fail are our screws or bolts. So we can remove the bolts, remove the holes, and this will simplify the meshing and the simulation very much. Finally, and this is very important, you should also think about how you want to create a simulation during the CAD modeling. For example, in this example, we wanted to test the under truck protection, kind of bumper. And for this simulation, we needed some faces to apply this boundary condition. And therefore, it's necessary to split this surface into some subsurfaces so that we can apply independent boundary condition for each of them. And last but not least, fuse as much as you can. This assembly, for example, you can fuse, I would say, everything to one single part. Yes, and that's basically what you need about mesh preparation and pre-processing. Another important thing is mesh convergence. And just to make sure everybody knows what I'm talking about. As you know, we at FEA, we are using numerical methods to solve these problems in a discrete way. So we will receive only results for displacement and stress for the nodes of our mesh. And as you can imagine, increasing the mesh density will increase the quality and accuracy of the simulation. But it's not like that increasing the simulation accuracy, or increasing the mesh size more and more will increase also the accuracy of the simulation more and more. It's another little bit different. In the end, there is a kind of minimum number of elements I need to get a reasonable result. And this is what we call a mesh-independent solution, or what we call a mesh convergence study. And the idea is to find out that using the fewest reasonable number of elements. And a very good tool is to analyze the stress at the chosen point, and then start with the coarse mesh, make it fine more and more, realize it, and do this until the results are not changing anymore. And this is a very good example. Here we have a very coarse mesh, first order, fast is generate. And now we have increased more and more the number of DOF, so we have increased the mass density. And here you can see, here we take a look at the maximum von Mises stress within the part. And if we increase the degrees of freedom, first of all, it's changing a lot. And from 200,000 DOFs, it becomes stable and converged, which means at this point, the mesh delivers a mesh-independent solution. And here you can see where we needed actually to refine the mesh. It's only here where we have a high stress region. And now we can use, for example, very coarse mesh, just add a local refinement here. And then the overall mesh size is just it's very small. It's between the coarse and moderate mesh, but we have the full accuracy. Great. So thank you very much for your time. And if you have questions, we can just write them onto the YouTube live stream and we will answer them later on. And now I'm very happy that my colleague Krishna have joined also today. And he will now give you a live demonstration and show you how to leverage our free simulation platform for Enduro Student India competition.
All right, so thank you, Milad, for this amazing explanation about the concepts of FEA. And hello and welcome everyone to this Enduro design workshop. And today we'll be talking a bit more about how to use Simscale to set up a suspension simulation for analyzing various stresses in your spring and the damper and different parts of a suspension. So before we jump into the simulation part of the presentation, I just want to give you a brief overview of the FEA process. So before you set up any simulation, you would need to make some hand calculations through which you can know your boundary conditions. You can derive a ballpark in which you want your displacements to be. So let's just look at some hand calculations that we've done. So first, I would like to tell you that we are simulating the front suspension of an ATV or an all-terrain vehicle. So basically what we do is we have a mass of 220 kilos, that is approximately that is the mass of a generic ATV, and we distribute it 60% at the back and 40% at the front. So that gives us a K value of 23.399, and this basically is a predefined or an experimental value of a generic ATV. And once we get the K value for the front suspension, we can just plug it into the force balance equation and hence derive our maximum deflection. So now we know that for the mass of the vehicle, the spring would deflect around 3.5 centimeters, and this gives us a good starting point around which we can formulate a parametric study. So what we'll be doing in this parametric study is we'll be making 3 simulations. One would be for 1 centimeter, the second one would be for 3 centimeters, and the third one would be for 5 centimeters. Now what the aim of this study is to analyze the stresses in the spring. Like as any designer or as any engineer would expect, the spring is the part of the suspension which undergoes the maximum deflection, and the maximum deflection would hence lead to a higher deformation, and higher deformation would lead to higher stresses in the spring. And you also must remember that the spring has the smallest circumferential area or the cross-section area, and hence the stresses go up. So what we are trying to do with this simulation is we are trying to limit our stresses due to a displacement to a value which is lower than the yield point, or a value which is such that the spring in the suspension does not plastify. So let's just take an overview of our simulation. So basically we make it we have a deflection at the damper, and here is our damper, and here is where we apply the deflection, and this is our spring, and this is the part which would be fixed at the chassis. So this would be limited in all degrees of freedom. So let's move on to the next step. This is basically the non-linear regime of steel. So basically what we want to see here is the non-linear or the plastic deformation in the spring gear, and this spring would give us a good idea where the maximum stresses are and what we need to limit with our simulation. Okay, so let's move on to the platform. Okay, So here we have our suspension. So this is basically split into three bodies. This would be our damper and the upper fixation. This would be our lower fixation, and this would be our spring. So basically what we are trying to do here is apply a deflection So we are basically trying to apply a deflection here, and it would be fixed to the chassis at these 2 points. So these would be limited in their degrees of freedom. And let's just move on to the next step. Let's create a mesh, and let's just make a fine mesh. The reason for making it fine overall is that we don't exactly know where the high stress regions would be. Once we have the results from our fine mesh, we can always make a mesh independent study where we can analyze the effects of the mesh on the result and also optimize our number of computing hours. So we can save a lot of computing time if we have an optimal mesh. But the purpose of this tutorial is just to show you how to set up a simulation by yourself, and you will see a detailed step-by-step for the same. Okay, once all this is set up, we can increase the number of computing cores to 8, and let's start it. Right, this would take some time to compute, so let's just look at a prepared mesh. Alright, so here we have our prepared mesh, and as you can see, if you zoom in a bit, you can see that the spring has around 15 elements across its diameter, and this seems to be a good first mesh, and we can proceed with the simulation with this mesh. Alright, so let's create a new simulation, and let's call it suspension sim. And the analysis type would be static analysis advanced, and we set the nonlinear analysis to true because we want to analyze the plasticity defects or the plasticity effects in the spring itself. So we need to set nonlinear analysis as true. Alright, so now we need to set the domain on which the computations would be performed. So this is basically the mesh we just created in the last step. So let's select it and save. And we can now see the topological entity sets. Now these topological entity sets need to be created by yourself, but in this case they have been pre-prepared for you just to show you where the topological entity sets are. You will receive a detailed step-by-step procedure to create your own topological entity sets. So just let's look at some of the entity sets. Let's select this and just isolate selection, and you can see this one is at the top of the damper, and this one, if we show all, would be at the fixation, as we can see here, and the slaves would be on the spring. As you can see here, this is the part of the spring, and this is the lower slave. So this is how we use topological entity sets, and these would be really helpful in setting up our further constraints. So the next step in our workflow would be to set up a constraint, and the first constraint would be between the damper and the spring. So let's call it upper bonded, and let's assign upper master bonded and lower damper slave bonded. So basically there is a general best practice involved here, that the master entity is always the entity undergoing lesser deformations. So as we know here, the damper would undergo lesser deformations than the spring. So that is why we assign it as the master entity and the slave entity as the spring. And let's save it. And we add a new constraint similarly between the fixation on the bottom and the spring. So let's call it lower bonded. And let's assign it to the lower master bonded and lower safe bonded. Now the next step would be to define a physical contact. Now as you can see, our suspension system has a physical contact between this cylinder and the cylinder at the inner face of the damper. If we can just show it. So basically at this face and at this face. So we define a new physical contact for these two faces. So let's just call it connection 1, and let's assign it to cylinder master physical and cylinder slave physical. Now we need to define our materials. So we can just import the steel from the library. That would be assigned to our damper and our fixation. Now the material behavior in case of a damper and our fixation would be linear elastic, because we do not want to see the plasticity effects, or rather we do not expect plasticity effects in the damper or in the fixation. An engineer can only imagine, like, if there is plasticity in the damper and the fixation, the spring would already have broken, so that simulation would really not be of any use to an engineer. So let's just keep it to elastic, because we are not going into the plastic regime of the damper or of the fixation. Alright, so let's go to the next step and add a new solid material. Again we add it as steel, but this will be, okay, let's add it again. Yeah, this, let's call it steel plastic, because we assign it to our spring in the end. So now we change the behavior to plastic, and we upload a file which defines the plasticity of the spring steel, and we just upload it. This file would be provided you in the step-by-step tutorial, and you could have a detailed look at it, and we can just look at it quickly here. So basically these are the strain values in the plastic regime, and these are the stress values in the plastic regime. So as you can see, it's around 5 E8, that is 500 megapascal. That would be our yield point for steel. So that is the point beyond which the steel or the spring steel would not jump back or go back to its initial state once it is deformed. Alright, so our next step would be to define the initial conditions, but here we just set it all to 0, because the initial state of our simulation is at 0 deflection, and we gradually define a deflection over time with a displacement constraint. So that displacement we will be adding as a constraint. So let's just call it displacement, and as a fixed value constraint. Now we know that the displacement is being applied at this point, and we also know that it is in the negative z direction. So we can just add a formula for it. Because we want to apply it gradually over a period of 1 second, we can just say minus 0.05 times t. So this would gradually apply a deflection in steps of 0.1 second. So 10 steps for a period of 1 second. And let's assign it to displacement. So this is how you can see that topological entity sets that you create after the meshing are a huge asset when you want to assign it to a particular constraint. Now let's define our second constraint. That would be the fixation. And it would be a fixed value. And what we want to do here is fix these 2 points in all 3 degrees of freedom, or all 6 degrees of freedom. So we just set all the displacements to 0. And we assign it to fixation. And the numerics is our next step. So we select the solver as MUMS. MUMS is basically a very robust solver when it comes to plasticity effects or nonlinear analysis. So it is a best practice to use MUMS for our case. You could also try other solvers like LDLT, PETSC, because you can always try and optimize the time it takes for a particular simulation, but MUMS is considered in general a more robust solver. So let's go to our next step, that is the simulation setup. We need to change the number of computing cores to 8 because our mesh is not too big, not too small, so 8 is a good approximation. And now we need to add result control items. So basically what we are trying to analyze from our results are the stress values in the spring, in the damper, and in the fixation. So we just add 3 new result control items. So the first one would be, let's call it min max spring, and let's assign it to be von Mises stress, and we assign this to the spring and save. And the next step would be to create another one similarly for our damper and for the fixation. Max damper, and we assign it again as von Mises stresses, and we assign it to the damper. Okay, now we need one final result control item which would show us the reaction forces on the fixation, because we are basically applying a displacement in our case, and what this displacement would do is create some reaction forces on our fixation on the point where our suspension is fixed at the chassis. So these reaction forces are very important to measure the deflections in the chassis itself. So hence we need to measure these reaction forces, and it would make sense to monitor them as well. So let's just add a new area control item. Let's call it RF as in reaction force, and stress, this would be force rather, and reaction force, and this we would be monitoring at this fixation here. So let's assign it to fixation and save. Okay, so let's just make a quick check whether everything is correct, and it seems to be all okay. And let's create a new simulation and start. Now this simulation would take in the ballpark of around an hour to complete, or maybe half an hour, but let's just look at a pre-prepared simulation and let's just look at the results. So we already have some prepared parametric study. So basically the three deflections supplied here are 1 centimeter, 3 centimeters and 5 centimeters respectively. So what we are trying to view with these images is the initial state, that is the transparent view of the suspension you can see here, and the final state in case of the 3 deflections. And the main aim of this deflection is to produce stresses in our spring, and these stresses are what we are mainly interested in. So as you can see here, a deflection of 1 centimeter and a deflection of 3 centimeter produces some high stresses, but it is still not in the plasticity range. It is around 1.5 E8, that would be 150 megapascal. This would still not plastify our suspension or our spring. So basically what this means is, if you apply a deflection of 1 to 3 centimeters, it is operating within a safe range, and it would immediately jump back to its initial state once the load is removed or once the load is relaxed. But once we look at our deflection of 5 centimeters, we can see that there are some high stress regions here in the spring, and they are even higher than our yield point. What we are analyzing here, 300 megapascal, is not exactly our yield point, but our yield point subjected to a factor of safety of 2. That is a good factor of safety, or a very conservative factor of safety we are analyzing here, but you could always play around with your factor of safety and follow standards for determining your safe range. Alright, so basically that is it. Alright, just as a last step, I would like to talk about the homework assignment that we've prepared for you. You can find it on our forum as well, and we'll be sending you this link tomorrow. And it basically enables you to simulate the deflection on a suspension system, and you can create your own setup and make a parametric study, make a mesh independent study, and you're free to do what you want. But there will be specific deliverables which will be highlighted in the step-by-step tutorial as well. And if you submit this homework assignment, you will be entitled to have a participation certificate from the workshop. And I think that is all from my side, and over to you, Milad.